Alrighty. The binomial situation. Do you remember the binomial from the last unit? It was a discrete model. So the binomial situation arises in situations of independent repeated trials in which each trial is either success or failure. That's the probability. Then if you recall, to calculate the mean equals NP, or expected value equals NP, right? I guess we did this, right? That's what we did. But expected value is basically another word for the mean. On average, what can we expect to get? So, here's a graphical presentation of the binomial with n equals 15 and p equals 0.4. So if we were to graph it, notice the shape, right? So as n and p get larger, it even becomes more smoother. Notice the bell shape of the distribution. Just looks something like that. This suggests that we can approximate the binomial distribution by a normal distribution. The advantage of this situation is we can save on a lot of calculation. I mean, if you only have to do one or two calculations, then by all means use the binomial. But if you want, suppose you have 600 trials, you need the probability to be x is less than 200, then you have to do 200 calculations. We don't like that, right? It's too much work. The normal approximation to the binomial helps us simplify such tedious calculations. These are the steps. Determine whether or not the normal approximation is appropriate. NP must be greater than or equal to 5. NQ must be greater than or equal to 5. Those are the tests. That's worth a mark on a test. When NP and NQ are not at least 5, both of them have to be at least 5. The probability distributions are either skewed to the left or skewed to the right and do not take the appearance of a normal distribution. When the above conditions are not true, the normal approximation cannot be used. The mean and the standard deviation must be estimated using, you know that formula. You're now learning the formula for a binomial situation for standard deviation. I do not have the proof, and my apologies to this student, I won't mention his name, who likes derivations. But I always just accept it. I've taken several stats courses in universities. They don't go in the detail. I imagine the more mathy, well, I took a mathy one too, and they didn't, I've just accepted it. Now, we need to do another step because we are adjusting a binomial which is discrete. We want to approximate a binomial which is discrete by a normal distribution which is continuous. We have to do a 0.5 adjustment. Note, there is always a 0.5 adjustment, a 0.5 adjustment. Yes. So notice, this is it's about as simple an explanation as I can make. So notice, if we have sort of a binomial situation and we're trying to fit it under a bell curve like this, well, the middle value is our value. So let's say this is 2, and the middle value here is 3. The middle value here is 4, etc. Notice, if I want the probability x is less than 4, I have to go to 4.5 to get the whole rectangle. So this is equal to the probability x is less than 4.5. So I can get the entire rectangle. Do you notice as if I have like a histogram and it's a binomial and I'm trying to get a normal distribution out of it, the smaller these boxes are, the more accurate they are, right? Right? And you can get a more accurate area by the smaller the boxes are. But if I want the probability x is greater than 5, then I'm going to have to go probability x greater than 5. I'm going to have to go to 4.5. Probability x is greater than 4.5. So there's this 0.5 adjustment in order to include the entire rectangle. So here's some examples. If it's less than or equal to 5, we have to, its probability is less than or equal to 5. We want to include everything in the 5 box, so we go to 5.5. If the probability is greater than or equal to 5, then x is greater than or equal to 4.5 because we have to go to include that rectangle. So if you can imagine the rectangle, here's 5, and I want everything to the right of it, right? Then I have to go to 4.5. However, if we want a probability x equals to 5, we have to go 0.5 below and 0.5 above, because if you can't look up 5. The area under a single point is 0. You need to create a range. Okay. However, if the probability is less than 5, right? We do not want the 5 included at all. We're going to have to go probability is less than 4.5. So if we want the probability x is less than or equal to 5, then we want the probability x is less than or equal to 5.5. Do you see the difference? Here we don't want any of the 5 box included. Here we want the entire 5 box included. If probability of x is greater than 5, then we want probability x is greater than 5.5, right? So we don't want the 5 included. We want everything to the right of 5, right? We want everything to the right. But if we want the probability x is greater than or equal to 5, then we're doing x is greater than 4.5. Okay? All right. Let's do an example. How many? Just 2 examples. Can you hang in there? You guys look really tired. Or is it me? Yeah, yeah. The probability of tossing a head with the weighted coin is 3. P equals 0.3. That means Q equals 1 minus 0.3. That's 0.7. If the coin is tossed 60 times, n equals 60, what is the probability? 10 or fewer. Is that including the 10?
Yes. Oh, yes.
Okay. Let's do A. We have to test. Test. This is step number 1 for an easy mark. Test to see whether normal approximation is appropriate. So, NP equals 60 times 0.3. That equals 18. That's greater than 5. Check. NQ equals 60 times 0.7. That's 42. That's greater than 5. Check. Therefore, yes. It's a yes. NA is appropriate. Yeah, this should be NQ. You're right. Thank you. Step number 2. Calculate your mean. Is NP equals 60 times 0.3 equals 18. We actually could have pulled it off right there, right? And sigma equals square root of NPQ, and that's the square root of 60 times 0.3 times 0.7, and that is the square root of 12.6. We'll just keep it accurate for now. So I'm not going to convert it to a decimal. So let's do number 3. Let's do a 10 or few. Probability x is less than or equal to 10. Yes, we want the entire 10 box to be included. Probability x is less than or equal to 10.5. Now we have our z-score, right? We just plug it in. I don't think there's anything to get excited about. Good? It's better than doing 10 calculations, right? Or 11 calculations.
Right, so you said P of x smaller than equal to 10 with P of x smaller than equal to 2.5. Is that smaller or equal to 2.5? The same as smaller than.
Oh, say that again.
So x is smaller than or equal to 10.5. Can we just write smaller than 2.5?
Yeah. Yeah. This is equal to, because the area under a single point is 0, so it won't affect anything.
Okay. But if that equal sign is on the left, then it matters because it's whether we choose 9.5 or
Here, yeah, it matters here,
I see.
but it doesn't matter there,
Okay.
because we've done the adjustment. But that adjustment's important. That tells us our adjustment. Okay. Oh, we're going to do part B. Okay, we're going to calculate exactly 20 heads using binomial model and the normal approximation. Okay, we're going to see how different are our results. Using binomial, we want the probability x equals 20. So we have 60 choose 20, 0.3 to the 20, just like in the last unit, 0.7 to the 40 is approximately 0.0937. Now using normal. So we want the probability x equals 20, but because we're using a continuous model, we're going to need a 0.5 below and above adjustment, right? So that's going to be the probability 19.5 is less than x is less than 20.5. Or less than or equal to whatever, it doesn't affect the calculation. So this is going to be the probability x is less than 20.5 minus the probability x is less than 19.5. Calculate your z-scores. Minus 18 over square root of 12.6. Z is less than, this works out to 0.7. I find that odd that such a thing would turn out to 0.7. 20.5 minus 18 divided by square root of 12.6. Yeah, because it's 0.704, so we round to 2 decimal places. So this is 0.7580 minus 0.6628, which is 0.952. So if you were to compare, it's the same to the first 2 decimal places. Oh yeah, thank you. So can you see they're pretty close? I mean, not exactly. Yeah. This one in this case is more tedious. Absolutely. Let's do one more example. It is estimated that 15% of will you remind me to give you your test back today? It is estimated that 15% of the Canadian population is undecided as to which political party to vote for in the next election. If a poll is conducted in 107, n equals 107, oh yeah, thank you. Let's see. P equals 0.15. Q equals 0.85, right? 1 minus 0.15. What is the probability that more than 100 of them are undecided? Let's do it. Does more than include 100? No, it does not. Because it's more than 100. So, 1, test to see if normal approximation is appropriate. Is there a smaller word for appropriate? Huh? NP equals 1007 times 0.15. That equals 151.05. That's greater than 5. Well, we know NQ is greater, but let's just calculate it. And that's greater than 5. Everything is greater than 5, therefore normal approximation is appropriate. Easy mark, right? Yes. How come? You have to use binomial. No. 2. Mean equals 151, right? Sigma equals square root of 1007 times 0.15 times 0.85, and that equals square root of 1, 2, 3. That's a mark. That's a mark. There's one mark for your adjustment. We want the probability x is greater than 100. That equals the probability x is greater than 100.5, right? Because we don't want the 100 included. Equals 1 minus the probability x is less than 100.5. 1 minus the probability z is less than 100.5 minus 151.05 over the square root of 128.3925. That's 1 minus probability z is less than, negative 4.46. What do you think? This is off the chart. What should this be? Equals 1 minus what?
Well, that's true because if the probability is 151 people are undecided, 100 of them, the probability of those people being undecided is. That makes sense. We didn't even need to do any of those calculations. Yeah, we did. No. I'm just saying.
Yeah. It's slightly shy. Can I explain anything better? Good. I'm having one of those days. Why, what's wrong with tomorrow? Is tomorrow the last lesson?
No, tomorrow's the library.
Oh, yeah. Okay. Tomorrow's the library. Why, do you want to do tomorrow's lesson? No, we won't. It's a long one. Be prepared on Monday for a lot of formulas. I'm even attached a section of the book for you.